This is section 2.1 on matrix operations. Just some basics out of the way first. We refer to an m by n matrix A as a matrix with m rows and n columns, and the individual elements in the matrix we denote by lowercase a with a subscript ij, where I is the row index, j is the column index. The diagonal entries in a matrix A are those where the row and column indices are the same, so like A11, A22, and so forth. These elements we call the main diagonal of A. A diagonal matrix is a square matrix where all the entries off the main diagonal are 0. So the only place you can have non-zero values is on the diagonal. So here are a couple of diagonal matrices. Notice that the key is off the diagonal. You have all zeros. So the main diagonal is just 1, 1, 2, 2, and so forth. 3, 3 in this case. So off the diagonal, off the main diagonal, you have all zeros. It's okay to have a 0 on the diagonal. We really don't care what's on the diagonal. We just want zeros off the diagonal. Here's another diagonal matrix. This one has a name. We call it the identity matrix. So it's a diagonal matrix because everything off the diagonal is zeros. And the zero matrix is technically a diagonal matrix because everything off the main diagonal is 0. We say that two matrices are equal if they have the same size, so the same number of rows, same number of columns, and their corresponding entries are equal. So the 1, 1 entry in one is equal to the 1, 1 entry in another. In general, the ijth entry in one is equal to the ijth entry in the other. We can compute the sum of two matrices. We can add two matrices together. This is defined if both matrices are the same size. So they have the same number of rows and same number of columns. And in this case, the ijth entry in the sum is just the sum of the ijth entries in each of the original matrices. So here's an example one that this sum cannot be computed because these matrices are not the same size. Here's one where we can compute the sum, and notice the 7 here is just the 3 plus 4. To get the 3, it's this 2 plus 1, and so forth. So to get the ijth entry over here, you sum the corresponding ijth entries in the two original matrices. We can compute the scalar multiple of a matrix in the same way we compute the scalar multiple of a vector. We just multiply each entry by that scalar. So here's an example. Multiply 3 times each entry in this matrix, and we produce this one. Your book lists some properties of addition and scalar multiplication of matrices. The first 3 are regarding addition. So you'll find that since addition of matrices is defined essentially the same as addition of real numbers, then a lot of those same properties carry over. So a plus b is b plus a. The second one allows you to associate the parentheses as you'd like, so that's the associative property. And if you add any matrix to the 0 matrix, you get the same matrix back. And then the last 3 were regarding scalar multiplication, and essentially these say that you can kind of stick the scalar wherever you'd like to, wherever it's convenient. It all is equivalent. Okay, let's move on to matrix multiplication, because matrix multiplication is not defined simply as matrix addition is. It's a little more complicated. It's not just multiplying the corresponding entries together. So here we go. If A is an m by n matrix, and the sizes are important here. So suppose A is m by n, and B is n by p. Okay, so that's the key. The number of columns in the first has to equal the number of rows in the second for the product to be defined. Okay, so if you have that situation, and we say that the columns of B are B1 through BP, then we define the product AB as the M by P matrix, and notice that the M is number of rows in A, P is number of columns in B. So we kind of always look to see if these inner dimensions match up. So the N here matches up with the N here, and that means the product is defined, and then the product itself, the dimensions of it, will be the first, the number of rows, which is M, by the number of columns of B, so it will be M by P. Okay, so how do we compute A times B? Well, notice what this says. It's the M by P matrix whose columns are A times B1 out to A times BP. That is, we want to multiply A times B. Then we look at it as A times each of the columns of B. Okay, so the first entry, the first column of the product is A times the first column of B. The second column of the product is A times the second column of B, and so forth. So notice that each column of the product, each column of AB, is of the form A times B1 or A times B2, and we know that when we compute A times some column, then we are taking a linear combination of the columns of A using the entries in the vector as the weights. So to get the first column of A times B, we're taking a linear combination of the columns of A using the first column of B as the weights. To get the second column, another linear combination of the columns of A using the entries in the second column of B as the weights, and so forth. Okay, so if we want to compute the product AB, where here are our matrices A and B, then we're going to do it as I just described. First, note that A is a 3 by 2 matrix and B is 2 by 2. So we check to see if the 2 here matches up with the 2 here, which it does. And then we look at the outer dimensions, the 3 and the 2, and that will be the dimensions of the product. So our product will be 3 by 2 in this case. All right, to get the first column of the product, it's A times the first column of B. So here's A, first column of B, 4, negative 1, and this is just a linear combination. So 4 times the first column of A minus 1 times the second column. And this is what we get. Do the same thing to get the second column of the product. It's A times the second column of B. Second column of B is 1, 8. So we take that linear combination, 1 times this first column of A plus 8 times the second column. Do that linear combination. And now we have our first and second columns of the product. And so we're done. There is A times B. There's another way to compute AB. Probably most of you learned this when you took algebra, college algebra probably. Notice that it's defined in terms of inner products. Right? So the ijth entry in the product, AB, is the inner product of row I of A with column J of B. So let's see how that works. So it's back to our same A and B. And to get the 1, 1 entry in the product, then it's going to be row 1 of A times column 1 of B. Actually, these are should not be A's. These should be I'm talking about the product here. So row 1 of A times column 1 of B. Do that inner product. So it's going to be 3, 2, inner product with 4, negative 1 to give you 10 in this case, and so forth. So to get to the 3, 2 entry of the product, it's row 3 of A times column 2 of B. Okay, so 5 times 1 plus 4 times 8 and gives you 37. And so there you go. You have the same matrix as we ended up with before. Okay, now you should note that since matrix multiplication is not defined simply, okay, it's not a simple operation like matrix addition is, then properties of real numbers that apply to multiplication do not follow over to matrix multiplication. They did with matrix addition, they don't with matrix multiplication. So, some warnings. If you're dealing with real numbers, A times B equals B times A. That does not hold true for matrices. For matrices, A times B is not necessarily equal to B times A. Of course, it sometimes could be, but in general, A times B is not equal to B times A. One reason is that sometimes they're not even both defined, right? Not even both defined. Maybe you can multiply A times B, but you might not be able to multiply B times A, and vice versa. However, even if they are both defined, you can't guarantee they'll be equal. So here's an example. Here's a matrix A times B, and we get this product. If we reverse the order, multiply B times A, we get a totally different matrix. Okay? So just because you can multiply both, compute both products, doesn't mean that they'll be the same result. So don't make that mistake. Second warning, for real numbers, if you know that A times B equals A times C, and you know that A is not equal to 0, you can divide both sides by A and end up with B equals C. Can't do that with matrices. If AB is AC, that doesn't mean that B equals C. Okay, here's an example of that. Here's a matrix A. A times B is this matrix. Here's A times C. Get the same matrix, but B and C are clearly different. And another one, the last warning, for real numbers, if A times B is equal to 0, you can assume that either A or B is equal to 0, or perhaps both are equal to 0. Not true for matrices. If you have a product of two matrices that equals a 0 matrix, that doesn't mean that A or B is equal to the 0 matrix. And here's an example of that. Here's matrix A times B, and we end up with the 0 matrix. But neither of these is equal to the 0 matrix. Far from it, in fact. Okay, some properties of matrix multiplication. You have the associative property, so you can move the parentheses around, but notice that the order that the matrices appear is unchanged. Okay, so we can't move we can't change the order that the matrices appear. Can change the order in which we do the multiplication. We can distribute either from the left or from the right. Here in numbers 2 or 3. Oops, back that. Oops, sorry about that. And if we have a scalar, we can move it wherever we'd like. And apparently I thought that was quite a important thing, since I put an exclamation mark there. Any matrix multiplied by the identity is just itself. Now notice that I'm assuming A is m by n here. So if I multiply on the left, I have to multiply by the m by m identity. Whereas if I multiply on the right, I have to multiply by the n by n identity. Okay. One other thing, the transpose of a matrix is computed by taking the ijth entry of the original matrix, and that becomes the jith entry of the transpose. So for example, If this is your matrix A, then I take the 1, 1 entry here, becomes 1, 1 entry here. 1, 2 entry becomes the 2, 1 entry, and so forth. I mean, perhaps an easier way to think of it is that the columns of A become the rows of A transpose. So column 1's 3, 1, 5, row 1 of the transpose, 3, 1, 5, and so forth. Or alternatively, the rows of A become the columns of the transpose. So here's a row, first row here, 3, 2, first column here, 3, 2, and so forth. Some properties of the transpose. If I take the transpose of a matrix, I'm back where I started. You can look here. If I take the transpose of this matrix, then I end up with A. Row 1 here becomes column 1 of A, and so forth. So the transpose of the transpose is the original matrix. Transpose of a sum is the sum of the transposes. Number 2. Can move a scalar around. Number 3. Number 4, kind of interesting. If you want to take the transpose of a product, that is the product of the transposes, but in reverse order. Okay, reverse order. So here's an example of that. If I want to compute the transpose of a product, AB, all right, so here's A, here's B. I want to compute their products, then take the transpose. So I compute the product, here it is, transpose that, and end up with this matrix. Or I could do it this way. Transpose each of them initially, but reverse the order that I do the multiplication. So here's B transpose, right? Here's B up here. So I take the transpose, that's here. Here's A transpose, and I compute that product, and I get the same thing as I did previously.